When we first started talking about solutions, I defined the solvent as being the component of which you had most in the solution, unless you had water, in which case water 99.9% of the time is referred to as the solvent. Water is the most important solvent. Water is an amazing solvent. Without water's properties as a solvent, life would not exist. We start off chemistry courses doing all kinds of chemistry where we have dissolved something in water. For many of you, your careers will be defined by solutions in which water is the solvent. And so it's worth an extra special little movie to discuss dissolving materials in water. Now, pretty much metals don't dissolve in water, so we'll worry about ionic substances and covalent substances. Ionic substances we have already discussed in our solubility, because some ionic compounds, the ionic bonds, are weak enough that we can consider them to be kind of like the hydrogen bonds in water, and they will dissolve in water. Other ones will not dissolve in water. Thus, we're going to split ionic substances right now into those that are soluble in water and those that are insoluble in water. Now, I trust you'll remember that those that are soluble in water do so because the cations are surrounded with the oxygen ends of water, making ion dipole forces. The anions are surrounded by the slightly positive hydrogens of water, making, again, ion dipole forces. What I didn't emphasize there was that that means that you've broken those ionic bonds. The cations and the anions have dissociated. They are broken apart. That means that in an aqueous solution, aqueous means water as a solvent, aqueous solution of ionic substances, you have separated cations and anions. This allows them to conduct electricity. We describe such solutions as containing strong electrolytes. A soluble ionic compound, when it dissolves in water, is a strong electrolyte. Now, of course, there are also ionic compounds that are insoluble in water. They're boring. Now, if it's not ionic, and it's not metallic, it must be covalent. And again, covalent substances can be soluble in water or they can be insoluble in water. Covalent substances, however, things like glucose, sucrose, etc., methanol, ethanol, they don't dissociate, so we call those non-electrolytes. Again, covalent substances that are insoluble in water, while they might be extremely interesting in their own right, for us they are boring. Now, right at the end of this little sequence, we're going to introduce a type of substance that is a covalent molecule, but it behaves as if it were ionic when you put it in water. And these, at least at the level that we're talking about this term, are acids. Acids are covalent substances that behave in aqueous solution as if they were ionic substances. For much of the rest of this video, I'm afraid I'm just going to be throwing facts at you. These are facts that you need to learn. So I'm going to talk about it, but I want you to print the thing out. I want you to look at it. I want you to write out, because writing is the best way to memorize things. Okay, and the first thing we're going to do, we're going to talk about the so-called solubility rules. Some ionic compounds are soluble in water, some are not. You need to know which are, you need to know which are not. Fortunately, it's not random. There are some rules associated with it that you just need to memorize. Okay, so what we're talking about for the next 2 slides we are going to talk about, here's an ionic compound. How can you look at it and decide is it soluble or insoluble? Well, the first rule is you look at your ionic compound, you identify the cation, and if that cation is ammonium or an alkali metal, so sodium, potassium, etc., it is soluble. At this level of what we're discussing, no exceptions to that. You see an ionic compound, it's got sodium in it, boom, you know it's soluble. You see an ionic compound, it's got ammonium in it, boom, you know it is soluble. Similarly, if when you identify the anion, it's nitrate, perchlorate or acetate, it is indubitably soluble. Those are the easy ones. 3a, if the anion is chloride bromide or iodide, so you've looked at your ionic compound, you've said, what's my cation, what's my anion? If the anion is chloride bromide or iodide, it's soluble, unless the cation is silver, lead, copper 1+, Hg2 plus or Hg2 plus, essentially silver, lead, copper 1, or mercury, in which case it's insoluble. If the anions fluoride, it's soluble unless the cation is lead, magnesium, calcium, strontium, or barium. So some interesting little issues there. Okay. If the anion is sulfate, it's soluble unless the cation is silver, lead, mercury, calcium, strontium, or barium. So you sort of memorize those exceptions. Now, what we talked about on this slide are generally, if the ion is this, it's soluble. Here are the exceptions, which are insoluble. Moving on to the last slide, the second slide, it's the other way around. If the anion is OH minus hydroxide, it's insoluble. The general rule is hydroxides are insoluble unless the cation is alkali metal ammonium, strontium, or barium. Now notice we've already said if the cation is an alkali metal or ammonium, it's soluble. So therefore that is obviously going to be an exception to if the anion is something, it is insoluble. So this part is a repeat of rule number 1. Okay, but it is important to note that if the cation is strontium or barium when the anion is hydroxide, then it is soluble. If the anion is sulfide, S2-, it is insoluble. Unless, now of course you already know some of those exceptions, because you know if the cation is alkali metal or ammonium, it's soluble. But what else? If the anion is sulfide, it is insoluble unless the cation is an alkali metal or ammonium. There's the ones we expect, plus the alkaline earth metal cations. Anion sulfide, insoluble unless the cation is an alkali metal or an alkaline earth metal, in which case it is soluble. And finally, if the anion is carbonate or phosphate, it's going to be insoluble unless the cation is an alkali metal or ammonium. So really I didn't need to put in that unless at all, because you already know if the cation is an alkali metal or ammonium, it is going to be soluble. Now let's take that whole dissociation bit and just discuss a few conventions. Okay, remember, soluble ionic compounds dissolve and dissociate into ions. They are strong electrolytes. So if we take sodium chloride solid and we add it to water, it is going to dissolve. And we can write that as NaCl, sodium chloride, in aqueous solution. But we know sodium chloride in water dissolves and dissociates. The dissolves is the aqueous part. It all dissociates into ions. So therefore we need to think of it, even when we see NaCl aqueous is written, which is a convenient way to write it, what we actually mean is that it's Na plus dissociated in aqueous solution surrounded by water molecules, and Cl minus in aqueous solution dissociated from the sodium surrounded by water molecules, separated ions. Calcium chloride in water. Well, all chlorides are soluble unless the cation is silver, lead, copper plus, or mercury. So calcium chloride is soluble in water. So we'll say, okay, when we put solid calcium chloride in water, it will dissolve, and we can write it as CaCl2 in aqueous solution. But of course we know that this is not actually representing what's actually there in solution, because it not only dissolves, as indicated by the fact it's in solution with that little AQ, but it dissociates. And calcium chloride dissolves and dissociates into calcium ions and 2 chloride ions for every calcium chloride. Sodium phosphate, it's soluble. All phosphates are insoluble unless the cation is an alkali metal or ammonium. This is an alkali metal, so therefore it's soluble. So when we put Na3PO4 solid in water, it dissolves, thus we can write it as Na3PO4 aqueous, knowing that of course it has dissociated into 3 Na pluses, NaPO4 3-. However, if we put solid AgCl in water, anion is chloride. If the anion is chloride, it's soluble unless the cation is Ag plus, right there. So therefore it's insoluble, so we would just write it as AgCl solid. Doesn't do anything. Calcium fluoride in water, it's insoluble, so we write it as CaF2 soluble. Cu3PO4 in water, we would just write it as insoluble as a solid, because all of these are insoluble. So if you've got ionic compounds associated with water, and we'll come back to this more in the second term, if they are soluble, you can write it as being an aqueous solution, knowing that they are dissociated. If it's insoluble, you just say, well, it's a solid, it's not in there. With water, it would make a heterogeneous mixture. Now, it would be remiss to leave this without doing a little calculation. How many moles of ions are present in 0.5 litres of 0.25 molar aqueous solution of calcium chloride? Well, we know molarity, of course, is moles over volume. So any time you have half a litre of a 0.25 molar solution, pop them in, and you can say I've got 0.125 moles. Okay, but that is 0.125 moles here of CaCl2. That's what the 0.25 molar solution of CaCl2 referred to, and the 0.5 litres was of that solution. Okay, but of course CaCl2 in water is not just dissolved in water, it has dissociated into calcium ions and 2 chloride ions. So therefore you're going to have 0.125 moles of calcium ions, because there's 1 calcium for every calcium chloride, but there are 2 chlorides for every calcium chloride. So if you have 0.125 moles of calcium chloride, that must be 0.25 moles of chloride ions. There's 2 chlorides in every calcium chloride. 0.125 times 2 is 0.25. So therefore, in total, how many moles of ions do you have floating around? Because each calcium chloride gives us 3 ions, we have a total of 0.0 or 0.375 moles of ions. The 0.125 moles of the calcium chloride times 3, because this splits into 1, 2, 3 ions.